Let me first thank the organizers for inviting me to my first FRAC meet and for the very generous hospitality they have been extending from the very minute I've stepped into this beautiful city. I know it's the fag end of the day, but it has been a day of beautiful talks, and I don't know how I will measure up to it, but my talk is self-organization of evolving cracks towards Voronoiness. Now, the key words here are to note are these self-organization, evolving cracks. So we are talking about cracks that are growing, and what is Voronoiness has been lightly touched upon by some of the speakers. I will speak of it at greater length at the right time. So there already exists a large body of literature on the formation and propagation of cracks and crack networks in connection to fluid transport. We heard a very beautiful exposition of it from Professor Alex Hansen. And then there are scaling laws in fracture interfaces and mechanisms of failure. And we have heard very, very beautiful talks on these areas. But there are certain mathematical aspects of crack networks that we feel in our group that also need to be looked at. So, for example, when you look at a crack network, for example, this is a mud crack. This is a crack network on a stone. This is on glass. This is on painting. And this is a shari, which is again a crack. It has been printed by what we call in India batik print. That is, it is coated with wax, and then the wax is cracked, and you dip the fabric with the cracked wax in different colors, and you get these, their cracks act as templates. So they all the crack networks look different. So the point is, we wanted to, how would you classify a crack network? One could speak of topology, which speaks of connectedness of the crack network, and you could sort of encapsulate it in what we call a NV combinatoric. What is N? So, if there is a node in a crack mosaic, then the vertex of N polygonal cells or crack beds, then that node is said to be of degree N and is termed regular. I will explain. Say, for example, if you look at this here, can you see my cursor? This is the cursor. I don't know. Cursor, how do you show the cursor? Which one do I press? All right. So if you look at this node, for example, this is a node to 4 regular polygons. So I will say this has a degree 4. This is also a regular polygon, but if I look at a node here, this is again a vertex of 6 polygons. So this is of degree 6. But you can have irregular nodes too. For example, this node here is the vertex of these 2 polygons, but not of this. So I will say it has a degree 2 as because this is an irregular and this is an irregular node. Similarly, look at this node here. This is also irregular in the sense it is shared by 3 regular polygons, but not this. So it has a degree N. So that is the way we assign N to a node, the degree N. What is V? Simple words, V is the number of edges to a polygon. So you can talk of any crack network in terms of this NV combinatoric. And you can also define a regularity index P, which is a ratio of the number of regular nodes, like here, to the total number of nodes. All right? So these are basic definitions. Now, in most convex polygonal crack meshes, you will find NV values ranging from 2, 4, that is N is 2 and P is 4, to 4, 4. And depending on whether the nodes are regular or irregular. A 2-4 topological description of a crack mesh is the signature of a Gilbert tessellation algorithm, and they are referred to as Gilbert cracks. Whereas on a triangular lattice, what we saw is a 3-6 combinatoric. The node was of degree 3 and it shared 6 polygons. So this 3-6 combinatoric is usually typical of a Voronoi tessellation and is referred to as Voronoi cracks. So you can combine the regularity index and N and V to write an algebraic equation like this, and you can draw a NV domain in which all crack meshes can lie. For example, P has to be 0 and P is equal to 1. This is one boundary. And for all closed polygonal meshes, the least you can have is V equal to 3, and you can go up to V equal to 2n. And this pink area is therefore the NV domain in which all our crack meshes should have their NV values. So, for example, this is a 2-4 index, and for that you would have an irregular crack mesh looking like this with 2 here and 4 sides. This would correspond to a 4-4 value, which would look like a crack mesh like this. And this would be a 3-6 value, and this is your Voronoi cracks. So our aim was to study all the crack networks that we see normally and see if we calculate their NV value, where do they lie on that domain? The motivation was that, say for example, clays. If clays of the same family have their NV in the same place? Do glass have their NV in somewhere else? So do materials show some signature belonging to a particular class in the NV domain? That was what we were looking for. So we studied various cracks, real and simulated. This is just an example of real cracks we did in a laboratory. This is laponite cracking under 2 different pH values. So finding their NV is a bit more complicated. You have to grayscale them, and then you have to find out their skeleton in a manner like this. So let's say this is the skeleton. Then you have to count the nodes and you have to count the vertices. But all this is only valid for convex polygonal cracks. If sometimes there are concave ones, and then it becomes a real problem, and we had to develop absolutely indigenous, programs. All of this we did. We had to develop our own programs to sort that out. And then, of course, there are the simulated cracks. These are all Gilbert crack tessellations of different distributions as regards their geometry. This crack is also simulated, but through what is called an iterative cell division, which is basically very simple. You take a cell, you take any 2 random points on 2 opposite sides, you join them by a line, you get 2 compartments. Again, you take for each of the compartments 2 points on 2 opposite sides, and again join them, and you keep on repeating it. And after several steps, you can see you get a crack system, which is fractal. This is a Voronoi crack. Again, it was generated by us. And this is a random distribution of Voronoi cracks. This has a Gaussian distribution. But when we did all of these and we put them on that NV, when we put all of this and put them on this NV, when we put it on this NV diagram, we saw that the cracks sort of all lay in this value between 2 and 3, and there was only one Voronoi which had a 3-6 value. All the other cracks, you can see Gilbert, Voronoi cell division, bentonite, laponite, starch, PDMS, which is a polymer, Then we did some oxides, tempered glass, brazen, mud. So we actually looked through all of these crack networks and we plotted their NV values and found them, most of them crowded like this. And at this time, there was also a work by Domukos and his group. And he called this form, this plane, he called it a platonic attractor, saying that most of the geological cracks also had an NV value here. But we were not happy because the cracks look different, right? When we looked at the cracks, they do look different, but we couldn't differentiate them from this. So they're not well reflected here. So we thought that it is not enough and mere topological description is inadequate. So what we did was we introduced geometric description. So we defined something called the angular defect. So what's that? So if it is a regular quadrilateral, we expect it to be 90, but a quadrilateral will have 4 different angles and each angle could be different. Let's call each of them theta I. So how much is theta I different from 90 in this case? So this you can do for any polygon, and that is when averaged over the entire mesh, you can come to some D average, which we call the angular defect. Also, we introduced something called a shape parameter, which is called the isoperimetric ratio. This is often used by mathematicians. And you can see defined like this, where A is the area of the polygon and L is the length. In this case, it's the perimeter. So defined like this, you can see that lambda will be 1 for a circle and it will be less than 1 for other polygons. And if you have needle-shaped polygons, then, very sharp, like shards of glass, then lambda is going to be very small. So in a layman's language, we may say that lambda is a measure of the roundedness or the geometry of the crack. So then we wanted to describe the polygonal crack meshes in terms of a 4-tupule, that is N and V were already there, and we introduced D and lambda, that is the geometric factors, but we can't plot all the 4 in one diagram. So this is an NVD diagram, and if you just look at how the D values differ, you can see that for all those cases that we studied, the D values are now a little bit more separated. And we did the same for the NV, now lambda space, and we see that the lambdas are again not as well separated as in D, but still quite separated. And we said that, okay, the topology geometry combinatory described via a 4-tupule NVD lambda is necessary to differentiate crack mosaics of different materials. This work was published in Physical Review A, but at that same time, see, this is the vast allowed domain, all right, of crack meshes, and yet when we looked at it, we remembered by that time we had seen columnar joints. Many of you would have seen columnar joints, and their crack mesh, if you look at a transverse section of it, is very, very hexagonal. So that means they have a NV of 3,6, and that would lie somewhere right up in one corner, whereas all the others are all clustered around somewhere else as far as their NV is concerned. But geologists say that these columnar joints at one point of time started off as random cracks. That means once upon a time, they were clustered in that group. And somehow over geological time, they had moved to that Voronoid point there. So that got us interested to finding out what is the trace of the path they would have followed and why. So these are pictures of columnar joints. These are in Genbudo Geopark in Japan. And these are what they look like, and this is what they look like if you cut them across like this. You can see a very, very regular hexagonal shape like this. So we wanted to study columnar joints. So how are columnar joints formed? So they are formed from cooling lava. So when lava cools, say for example, this is a schematic, this was lava, let's say, and as it comes in contact with air, it cools and it starts cracking to release its thermal stress, and you get random cracks like this. But now what I am showing here is a longitudinal section of how the lava, how the cracks propagate in the vertical direction to ultimately form the columns. So what you see here is this cracked front, this cracked tip here is represented like a conduit here, and the bed size here is basically a column of uncracked bed rock piece. And again, you have another cracked front. So this is it. So what you see in this longitudinal section is like cracks which tessellate the surface into columns of different widths. Now what happens? When a crack is formed, then the cold air from outside enters. First of all, there is cooling happening here. And then cold air also enters the crack, and it starts cooling these columns from the sides, from their interfaces. And you know, the hot air from above goes up. So in these, you have convection currents. And these masses of molten lava, they cool not only from the top surface, but as the cracked front has air circulating it, they cool also from across the cracked faces in this direction via conduction. So there is cooling by conduction and convection. However, depending on the width of the crack, you can see that a thicker, fatter crack column will have a higher temperature in its center than a thinner column. And so the point we are looking here is that there is no reason to assume that one crack will, you know, unless if I assume that they're all homogeneous in the transverse plane, there is no reason to assume that one crack will propagate more than the other. So we can assume that they are all propagating at the same plane here. And the question here is, in our next time step, let's say, where will this crack move? Will it move straight down, or will it change its direction? So that is decided by the isothermal lines here. So the isothermal lines, because of this unequal temperature distribution between the fat columns and the thin columns, the density of the isotherms here at the face of the crack columns here is different. And this particular cracked node is therefore acted upon by the thermal stresses of its neighboring columns, and it's going in a next moment of its movement, it is obviously going to move in a direction in which it can release its thermal stress most easily, and that will be in the direction of the steepest gradient of temperature. So if there is greater crowding here, this crack, instead of moving down like this, will change its direction. So in effect, what happens? So we are looking at this mechanism which enables a crack which could have been, which started as random. Ultimately, how can it change its shape and become hexagonal? So that's what we are looking at. So we simulated it like this. So let's say this is a crack node, all right, which is shared by the adjacent columns like this, and each column exerts its thermal stress so that this node actually is, its movement is going to be decided by the resultant effect of the thermal stresses of all the neighboring polygons with which it shares itself. So let us say that we don't know which are the centers of the thermal centers, heat centers of these pillars, but let us assume that they are the centroids, And so we take the distance connecting the centroid to the node as di, where I runs over each of the neighboring columns. And then we say that in a particular time, the amount of movement that this node will make in, let's say, a direction dn, where dn is some I, will be some fraction of dn. So what is that fraction? That fraction is some correlation function where you can see d average is the average of all the d distances of all the di's, and therefore that takes care of the neighbors, all the neighboring polygons. And d max is the maximum length here, and it is written in such a way that when d max is equal to d average, you can see that this will become 0, and therefore there will be no further delta x. And that means in the next and next time steps, it's just going to move straight vertically down. So how does it look like? Yes? Oh my God. So how does it look like? Oh, you can see it playing anyway. So this is the node which is moving that way. And I don't know, I'll just click it here. And you can see that what was irregular is not slowly changing its shape to the polygonal, the hexagonal things. All right. So next what we do is we come to what we had simulated. So these are our simulated columnar joints, which look very similar to what we see in nature. And we picked out single columns to show that what began as a different shape ultimately grows into a hexagonal thing like this. So all this was fine, and our journey to answer our question that how does it move on the NVD diagram. So if you start from here, it reaches the Voronoi point. We saw like this. What was important to note was that the area distribution does not change with time. These are time steps. However, the theta, the average angle of the polygons, they changed and maxed around 120 degrees. That is, they are becoming more and more Voronoi-like. So the point is, if they want to be more Voronoi-like, one would expect that they want to do that, and that would mean there is some kind of energy minimization. So we take a little section of it and assume that it is moving, penetrating a distance dz in time dt. So what could be the total energy contribution? We say that there is an elastic energy, and E0 here is everything else apart from elastic energy and fracture energy. There could be other contributions to energy, so let's call that E0. This is elastic energy. You can see that this is the volume of any particular bed, okay, where dz is the depth of it, and therefore gamma is elastic energy per unit volume. And fracture energy, that means to open up a face, you just calculate what is the total length times dz is the total amount of fracture space opened up, and eta is the fracture energy per unit area, and therefore as per unit length you can write the energy functional like this, and it seems that it should minimize, otherwise why should it propagate like this? Remember here A and L we can write in terms of lambda, our shape parameter, because it was defined like this. So having done that, we actually, our simulation enabled us to plot L for every time step of the entire mesh and lambda for the entire mesh, and we saw that it followed a power law like this, and when we put it into the energy expression, we ultimately found that the energy follows a law with lambda in this manner, where alpha and beta we could calculate. It is related to our BL and B lambda here, and for beta we found it is 0.3 here, and lambda, the shape parameter for our mature rocks, was 0.75. What do we say mature network? When the shapes don't change anymore. So when you plotted E versus T following this, we got this curve, which actually another group, Jagla et al., they had done this similar things, but they had worked with Monte Carlo simulations, not taking into factor the actual mechanism. That's what we thought. So now I come to the other point, which is Voronoiness, which we had spoken of. Voronoi patterns are very often seen. You can see this is in this is permafrost, this one. This is dragonfly, and this is Voronoi pattern seen in Mars. So the point is, Voronoi diagram, somebody mentioned, I think, that it is what is so great about Voronoi diagrams, that if you have a seed, every Voronoi diagram has a seed. It could be a seed of thermal stress, of moisture, highest moisture content. It could also be the center of mass. But all the space inside that polygon is, all points inside that polygon is closest to its own seed rather than to any of the other seeds. Voronoi diagrams are really fascinating, you know. If you're a football fan, I'll just take 1 minute because I was so engrossed. Like, you know, I really saw that Barcelona and all that, they are great fans of football. So their managers, they take drones and took, you know, pictures, movie pictures of how Messi and all they play. And in the football field, the 11 players are playing in such a way that the field is entirely always divided into a Voronoi-like pattern, when each of the 11 players acting as seeds, so that the field is sort of covered all the time, you know. So apart from that, it is used in many things. Basically, it is an optimization of some quantity, whether it is space, whether it is energy. So Voronoi diagrams are very important. How do you generate Voronoi diagrams? So you take some random seeds, and you do a Delanoid tessellation of it. Delanoid triangles are duals to Voronoi triangles. And then after you do the Delanoid triangles, you draw circumcircles. And then you take the centroids of it, and then you simply join those centroids which share an edge of the Voronoi triangle. And what you get is a Voronoi diagram like this. So that's all right, but what about real cracks? So for real cracks, we did a skeleton of it. We took the centroid of those polygons because we really don't know which is the seed. And then we did the Delanoid triangulation, and we did the circumcircles. And these are some of the real cracks that we worked with. And you can see here that some of the Delanoid, you know, circumcircles are marked in red. Why? Because this is not a perfect Voronoi, as because in a perfect Delanoid triangulation, it should not contain any other seed. Those that contain a seed, they have been marked with red. So you can define what a Voronoi diagram is by defining something, the number of non-empty circumcircles divided by the total number of triangles. However, look here, this mud crack and this honeycomb, both are, according to this, they are perfect Voronois, but they are not equal. So what we did was, the question comes, how good is a crack to a perfect Voronoi, or how much is it deviated from a Voronoi? So in mathematics, there is a Hausdorff metric which is defined, which if you have two sets of points which belong to two meshes, let's say A and B, you can start by drawing lines between A and B and finding out what is the biggest length between them. So here you have ds, and you can do the same for going from B to A, and you get here the largest length is D11. So the bigger of D6 and D11 is your Hausdorff metric. So we calculated our Hausdorff metric, and in terms of pixels, the mud crack was 14 pixels. That means if the Hausdorff metric is 0, it's a perfect centroidal Voronoi. This is not a perfect centroidal Voronoi, but it goes to Voronoi-like tessellation. I will very briefly, if you give me 3 minutes, I'll complete the top here.
Sure. You are consuming your time for questions. It's your choice. 3 minutes.
I will just take this example of wetting and drying cycles that Lucas and his group had reported long back, where they had said that if you repeat on mud cracks, cyclic wetting and drying, then T junctions gradually change into 120 degrees at the junction points. So we did something very similar to this columnar joints, except here the what's happening, it is instead of thermal stress. So when you have drying, there is desiccation, and the center of the pits are points of highest moisture content. And so there is desiccation cracks, and we did a spring network to show that the node is as if related to all the polygons it shares with a spring which has a natural length d0. And every time there is a drawing, it shrinks by a certain amount. N is a time step, so how much it shrinks is determined by its value of the spring at its previous time step. And when you wet it, what happens? It swells, it relaxes a bit, and it goes like this. And the amount was calculated and all that, so this is not important. And we again found that the energy decreases with time. So, and not only that, before you could stop the wetting drying cycles, they look like this. The stress distribution was like this, and after repeated wetting drying, they took this Voronoi shape, and the stress distribution became like this. So this is what I wanted to tell you. And once again, we calculated the Voronoi. We wanted to see how good a Voronoi they were, and obviously there were some. At the beginning, they were more red, and certainly they were less red after that. And we plotted the P and the Hausdorff metric. You can see that it is certainly going towards Voronoiness as the values are falling. So this is not important. There are some other laws for which are existent for polygonal meshes. Our simulation could reproduce them. This is also a paper by Ruhul in Chaos and Solitones and Fractals. And so this is another work, another example, but this is completely different. This is another system, salt pliers. You would have seen Ruhul as a poster on it. Ruhul is my scholar, by the way. And so what is the takeaway? It seems that dynamical crack mosaics tend to form Voronoi-like polygonal mosaics in equilibrium in order to optimize some property. In our case, it is broadly elastic energy. And with this, I wish to thank my collaborators. This is basically all work done by Ruhul Haq. He is here in the audience. Atish Mitro is our mathematician in the group. He works in Montana Tech in USA. Anamika Roy, some of you met. She's also one of my PhD scholars. Sujata Tarufdar is like a touchstone for us. Everything we do or say, even if she's not actively involved anymore, we share with her. And I'd like to thank you for your great patience. Thank you.
Thank you very much. Thank you.